Okay, so here we go with part 3 of Unit 4 for Calculus class. This is our last week before our final exam for this unit. There is a reminder at the top of this worksheet again about the situation where if you're trying to minimize a function, for example, and only find a maximum using your first and second derivative tests, make sure that you look at the endpoints for potential solutions. And we mean endpoints within the domain of the particular function for a potential solution. Again, we don't often see that, but it's good to keep that in the back of our mind. And in this video, I'm going to try my best to answer these questions in real time so that you can get a feel for the rate at which I would expect you to complete a problem like this. In this problem, we're told to find positive numbers x and y that satisfy the equation x times y equals 12, such that the sum 2x plus y is as small as possible. So I notice that the phrase as small as possible is given to us. That tells me that this description is talking about our objective, and the equation associated with this request is 2x plus y. So right off the bat, I'm going to say that the objective function is that 2x plus y has to be as small as possible, and I'm going to say that that sum is z. So our objective function, z equals 2x plus y. Now, as we look throughout the rest of the problem, we're told that one requirement is that x times y has to equal 12, and that's going to act as our constraint. Since there's an infinite number of numbers we could test for x and y, we could create a small result as we want for z based on any x and y value that we compute, but by limiting x and y to produce a product that's equal to 12, that acts as a nice constraint for us. Often we solve for a single variable, so I'm going to say that y is equal to 12 divided by x, and that's going to allow me to rewrite this objective function. It's also worth noting here within our constraints that x must be greater than 0 and y must be greater than 0. We were told that we're dealing with positive numbers. That doesn't really have an impact on the equation per se, but it does help us in a situation like this to identify our endpoints. So if we find, say, a maximum after using our first and second derivative tests, if we find a maximum to this equation, but we're trying to actually find a minimum to answer the problem, well, then we would go to our endpoints here and look at all x values that are positive and y values that are positive. So anyway, in this objective, we now have the equation 2x plus 12 over x. This way we've got a single equation in terms of one variable. And then I'm going to find the derivative. And we're going to find this derivative in terms of x. With practice, I've learned this little shortcut. When we have 12 over x or any constant over x, the derivative will increase the denominator's power by 1 while changing the sign in front of it from positive to negative and vice versa. Now, once we have the first derivative, we're particularly interested in when this first derivative equals 0. And when 0 equals 12 minus x squared, we can say that 12 over x squared positive is equal to 2. I've done that by adding to both sides. We also know then that 12 is equal to 2x squared by multiplying x squared back to the right. 6 is equal to x squared, and x would be equal to the square root of 6. Don't bother with the negative square root of 6 because, as we were told before, x must be positive. So this x value locates a critical point, the position where we're either at a maximum or minimum, since we have a derivative that's equal to 0. Although I guess it's possible to not have a maximum or a minimum point either. So let's verify what's happening here. If we investigate the second derivative, then that'll tell us about the concavity of the function, and once we know the concavity, we can confirm whether this x value produces a maximum, a minimum, or neither. So I'm jumping to the right here once we had our first derivative calculated so that I can calculate the second derivative. This first term goes to 0, and our second term is going to become positive 24 over x cubed. I think I forgot to mention in that shortcut from before that we do still multiply this exponent times the coefficient, 12 in this case. So 2 times 12 gave me 24. I changed the sign to positive, and I increased the denominator to 3. The degree of the denominator, that is, to 3. Now, I'm not so interested in when this second derivative equals 0. I'm more interested in when this second derivative is evaluated at the target from before. So what's happening at the square root of 6? Is the second derivative positive, negative, neither? Because that value will help me understand the concavity at that point. Well, 24 over the square root of 6 cubed essentially creates a positive number divided by another positive number. And so I know that the end result is going to be greater than 0. And so mentally I'm thinking, well, what happens when our first derivative is 0 but our second derivative is positive? Well, that creates a point at the bottom of a U shape, and therefore a minimum has been found. So one last thing that we can and should do in this case is find the y value that goes with this x value. And we were calculating our y value in terms of x earlier. So y is equal to 12 divided by x. In this case, x value is the square root of 6. I'm okay with this as a result. We don't need to simplify any further. So we'll call x equal to the square root of 6, and y equals 12 divided by square root of 6. And those are our two positive numbers that satisfy the equation x times y equals 12. And the sum of two x's plus one y is as low or as small as possible. So in problem number 19, we're asked to find the location of point P that exists on the line y equals 3x that is closest to the point 50, 0, and it goes on to ask what is the least distance between P and 50, 0. So locate the point and then calculate the distance between them. Well, this two-part question is nice because they come right out and talk about the phrase least distance, and so that gives me my objective function. So the objective function has to be the distance equation between this static point, this single coordinate, and then point P, which is dynamic, and it moves along this line. Now, the fact that this point is static sort of helps with our constraint function, but really the benefit here is that we're being told that the point has to lie on this line. Sometimes a sketch of the situation is helpful to see. So if I draw an xy axis over here, scaling is not going to be great, but let's say that this is the point 50, 0, and then we've got this line here that represents y equals 3x. It's a line with a slope of 3x. Again, scaling's not that great. Somewhere on this green line is going to be a point P, so that the distance between P and this point is the smallest. Now clearly, if we didn't have this restriction, if we didn't have this constraint, we could pick any point, say right here, and that would be pretty close to point P. Or maybe we can pick this point, and that would be pretty close to point, I'm sorry, not point P, but this point on the line, 50, 0. But we can't just arbitrarily pick values that are super close to that point, because that really defeats the purpose. We're being told that the point has to exist on this line, and that is our constraint. Now, if you know anything about geometry, you might have an idea of where the point should exist. I'll leave this here as a bit of a hint, and let's see if we can actually locate that using some calculus. So back to the word problem. We've identified our objective to be the distance between point P and this point 50, 0. So that's our distance formula. And we need x 1 minus x2 squared plus y1 minus y2 squared, and the square root of all of that. This is essentially the Pythagorean equation using coordinates instead of side lengths. Now the constraints we're dealing with are that, number one, the y coordinate, and we can call this y1 or y2, you'll see why in just a second. The y coordinate must be equal to 3 times the x coordinate. That's what the definition said. We're also told that one of our x coordinates in this formula has to be 0, and the y coordinate that's associated with that has to be equal to, whoops, I got those backwards. The x coordinate is 50 and the y coordinate is 0. And so if we say that x1 and y1 are 50 and 0, then I might come back here and say that y2 is the same as 3 times x2. Using these subscripts isn't necessary, but it does help see where these components are going to go when we rewrite our objective function. For example, I'm going to change y1 to 0, I'm going to change x1 to 50, I'm going to change y2 to 3x squared, and x squared by itself, well, that can stay as it is. I'm not x squared, but x2. That can stay as it is, and now when we rewrite this objective function, the entire thing would be written in terms of just x sub 2. So as we do that, we'll be left with d equals, I'm thinking about this a little bit more carefully here. Doesn't matter the order that you subtract in, but I'm going to modify this equation just a little bit. Just because when I square binomials, I tend to like to have the constant, the numerical value, at the end instead of at the beginning. x2 minus x1 squared is going to be exactly the same as x1 minus x2 squared. The two results are identical. So I'm just going to reverse these so that I have x2 minus 50 squared plus 3x sub 2 minus 0 squared. Again, I've made the replacements from the constraints, and I'm just more comfortable having the numerical or this constant value at the end of the binomial to square it. Well, then the distance is going to be the square root of, and I'm going to drop this subscript notation now as well. It's going to be a bit distracting to me when I write x sub 2 with a squared symbol after it, so I'm just going to call this x from here on out. But x minus 50, if that quantity was squared, that's going to leave me with x squared minus 100x plus 2500. Again, I just FOILed this in my head. And then at the end, I've got 3x minus 0. Well, that's just 3x, and 3x squared, the quantity 3x times itself, is going to be 9x squared. So we can combine like terms, and we now have the square root of 10x squared minus 100x plus 2500. All of that underneath the square root. Okay, so we've got a nice objective function that's been simplified, and certainly we can calculate the derivative. We could make it a little bit easier on ourselves if we consider 10x squared minus 100x plus 2500 as an entire group that's being raised to the 1/2 power. Then we could apply the chain rule in order to find the derivative of both sides. But I'm going to let you in on a little secret here. One thing that we could also do is simply square both sides of the equation back here. And if I squared this side and square this side, that's perfectly legal. That's keeping the equation balanced. And what we now have is d squared, or distance squared, is equal to this nice simple polynomial. And we shouldn't be too put off by that, because in the next step, when we calculate our derivative in terms of x, well, we've got the skills to handle that. Unfortunately, the derivative with respect to x has a differing variable than d here, so we'll have to use implicit differentiation, but that's not too bad. Our derivative is now 2d times dd dx, and that's equal to 20x minus 100. Calculating this derivative is much easier now that we don't have to use the chain rule. And the real benefit is here. If 2 times d times dd dx is equal to this equation, and we're looking for critical points of our derivative function, then that means that this derivative is going to be equal to 0. And regardless of what 2d is, well, that 2d times 0 will also be 0. And we've got 20x minus 100. And so when does 0 equal 20x minus 100? Well, that would be when 100 is equal to 20x, which means that this occurs when x is equal to 5. And we think we've got a solution here. We think that the position when x is 5 is going to produce the minimum point or minimum distance between that point on the line and the point 50, 0. Well, here again, to verify that, we'll use a second derivative. And I'll apply that second derivative at this point. So I want the derivative with respect to x of, and what it was before, I'll just use blue ink to be consistent here. It was 2d dd dx, and that was equal to 20x minus 100. And so when I apply the derivative with respect to x to that, we will be well on our way. In fact, in this second line, the derivative with respect to x of 20x minus 100 is simply 20. The only challenging computation we have is this guy right here, which is technically a product rule, so we'll be careful of that. All right, so the derivative of the first function would be 2 dd dx times the second function. All right, so just a quick recap before I move on. This is the first function and the second function I was talking about. So the derivative of 2d would be just 2, but since the variables disagree, we have to call this dd dx. Now the second function is dd dx in and of itself. And to that we'll add the first function, 2d, times the derivative of the second function, which is going to be d squared d dx squared. So we're essentially finding the derivative of a derivative, which is the second derivative. And if we simplify a little bit, this dd dx times this dd dx makes our second derivative. So 2d squared d over dx squared plus 2d d squared d dx squared. That still equals 20. And since the second derivative notation, d squared d over dx squared, is a common factor, we can say that d squared d over dx squared. Now I'm going to factor that out to be left with 2 plus 2d, and I'm going to divide that to the right-hand side just to isolate this all in one step since I'm running out of room. And now I've got 20 over 2 plus 2d. Now, keep in mind that we don't actually need a numerical result for this derivative. We just are hoping to find a positive second derivative here, because a positive second derivative at this position will determine or indicate that we've reached a minimum point. And the d value in both of these equations, and I think I failed to emphasize that back here, this is the distance. This is a calculated distance when, in this case, x is equal to 5. So if I needed to this d value after all, even after I made the substitution of 0, if I needed this d value, I would just calculate the distance based on x at this point, and I can do the same over here. The distance based on this x value, and therefore its y coordinate that goes with it, I could calculate that distance using the distance formula. But I'm not going to, because the number 20 is a positive value. Distance is always a positive value, so 2 plus twice that distance is also going to be a positive value. And when I have a positive number divided by a positive number, I end up with a positive result. It's going to be greater than 0. And so that's enough to confirm that a minimum has been found. So the minimum distance will be found when x is equal to 5, and when x is equal to 5, y is equal to 3 times 5, which is 15. So we're talking about the coordinate 5, 15. The distance to the coordinate 50, 0 is at a minimum along the line y equals 3x. So that's a good answer here. The second part of the question did ask us to find the distance. So the square root of x2 in this case is 5. So 5 minus 50 squared plus the y-coordinate, which is 15, minus 0 squared. Well, I'll just go to the calculator for that. We want the square root of, try that again, 5 minus 50 quantity squared plus 15 minus 0 quantity squared, and that distance appears to be 47.4342. 47.4342 units. Now, the alternative to using this implicit differentiation, I know some of you may have gotten either a little confused or sidetracked from here. The alternative, of course, was to do what I said before and call this the quantity of 10x squared minus 100x plus 2500, that group raised to the 1/2 power. And I did work through that in a set of notes in the past. So here's that expression, 10 squared minus 100x plus 2500 to the 1/2 power. In using the chain rule, where we bring down the exponent, leave the inner function alone, reduce the exponent by 1, then multiply by the derivative of the interior, we end up getting this first derivative computation here, and ultimately rewritten this way. The check for the second derivative is where this gets to be particularly challenging. Could you imagine finding the second derivative of this equation, or the second derivative of any one of these forms of that first derivative? That's where it gets to be a bit challenging, and I personally like this notion here, utilizing our implicit differentiation, because while it was, albeit a bit challenging or unusual to see this second derivative take shape, I think using the implicit differentiation method here is a lot better than the alternative of incorporating the chain rule along with the quotient and product rules again. So this video is getting lengthy already. We just did 2 problems and I talked a lot through that. I'm going to pause, or I'm actually going to stop this video and create a second one to get through the next 2 examples. Thanks for watching.